waiting for a few minutes. Okay. So they'll come in if they want to. We wait for the go from the big guy, big organizer. And, you have a price for nutrition? No price. So that's usually the only question that you get. The price. Aurélien, t'as sonné? Okay, so let's resume. Welcome everyone for the open session, open problem session. Just a few words before. I just want to say that we received 10 submissions for this this session, and we have accepted 5 of them. So there will be 5 talks, or maybe 4 because one is missing. We'll see. And yeah, and so the first speaker is Mérieux. And oh yeah, you want to open it or? So I don't know. How do you? Oh yeah, great. So it works. So Aurélien, Moritz, the floor is yours.
Yeah, thank you, and thank you all for coming. I will present some open questions on the fixed parameter tractability of certain sonotope problems. And this is based on joint work with Vincent Fröse, Christoph Hertrich, and Martin Scutella. So I will start by introducing sonotopes, and then I will talk how they relate to certain neural networks and how we can interpret certain verification tasks of neural networks in terms of these sonotopes. And then in the end, I will state the questions regarding the computational complexity of these problems on the sonotopes and therefore also on the verification of neural networks. So first, for 2 polytopes P and Q, the Minkowski sum of these 2 polytopes is simply the set of all the points x plus y, where x is in the polytope P and y is in the polytope Q. And a sonotope is then the Minkowski sum of finitely many line segments. So if we're given m vectors, then the sonotope is given by the Minkowski sum of the line segments that are spanned from 0 and these m vectors. And here on the bottom, you can see 3 line segments, and if we add them up, then this sonotope on the right results as their sum. So what does this do? What does this have to do with neural networks? So let's consider a ReLU neural network with 1 hidden layer, and let's assume that we do not have any biases. Then we have m ReLU neurons. Each of them compute first a linear map, and then take the maximum of 0 in this linear map. And we have an additional output neuron that computes a linear combination of these ReLU neurons. And the map computed by such a 1 hidden layer neural network is continuous and piecewise linear, as it's simply the composition of such functions. And since we do not have a bias, the map is also positively homogeneous. So we can scale it doesn't matter if we scale the input with a positive scalar or the output with a positive scalar. And since it's positively homogeneous, we can also assume without loss of generality that the output weights of the neural networks are either +1 or -1, because everything else we can just pull into the input layer. And this means also that I can now write the function as the sum over all the neurons that have a positive output weight minus the sum over all the neurons that have a negative output weight. And these 2 functions here, they are now both convex, since they're simply a sum of convex functions. And there's a nice duality going on between functions that are continuous, piecewise linear, convex and positively homogeneous, and polytopes. Namely, every such function I can write as the maximum of finitely many linear functions. And if I now take the coefficient vectors of each of these linear functions, I throw them into the dual space, and I take the convex hull of these coefficient vectors, I obtain a polytope. And this polytope encodes the complete function. So this map is a bijection. The polytope uniquely encodes the function, and the map also preserves some structural operations. So the addition of 2 functions now becomes the Minkowski sum of the corresponding polytopes, and taking the maximum of two functions corresponds to the convex hull. So let's now apply this bijection to our convex function that are computed by the Mérieux network. So first, I can simply pull the map into the sum and now obtain the Minkowski sum of these polytopes. And the maximum of 0 and such a linear function simply corresponds to the convex hull of the 0 vector and this linear coefficient. So now we have a Minkowski sum of line segments, which is simply a zonotope. So this function computed by the Mérieux network corresponds to two zonotopes, one for the positive and one for the negative part. And now I want to talk about verification. So by this I mean we're given the weights of the neural network, and then we're wondering what can we say about the function that this network computes. And for example, we would like to know what is the output range of a certain input set. And the very basic question that you can ask is if the network somewhere attains a positive output value. And translating this to the polytopal world, this is the case if and only if the zonotope corresponding to the positive part is not fully contained into the zonotope corresponding to the negative part. This is a problem also known as zonotope containment. And if we now assume that we only have positive output weights, then the Lipschitz constant of this function with respect to the p-norm precisely corresponds to the point in the zonotope that has the maximum p-norm. So deciding the Lipschitz constant of this network is equivalent to the LP maximization on zonotopes. So both these problems, zonotope containment and LP maximization on zonotopes, they're both known to be NP hard, but polynomial time solvable in a fixed dimension. So the runtime of both these algorithms is roughly m to the d that exists. And the question that we're having is if these problems, if they're really tractable in small dimensions. So if they are fixed parameter tractable with respect to the input dimension. So here the polynomial that we have in fixed dimension, here the degree depends on the input dimension, but what we want is we want to have an algorithm that solves these problems, and the superpolynomial runtime of this algorithm only depends on the input dimension d, but is a polynomial in the number of line segments or in the number of Mérieux neurons m. And the degree is independent, is constant. And these problems, they not only correspond to the verification of simple Mérieux networks, but they also independently appear in other fields such as robotics and control theory, pattern recognition and signal processing, and also political science and economics. So we believe that settling the complexity status of this problem is of interest across various fields. And that's all I wanted to say. I thank you a lot for your attention.
Any question in the room? No, usually we ask whether there's a price for solving it, but you told me there's none. And do you have any idea of how to you could tackle this question here? Any suggestion? Any?
One idea, I mean, this is something that we're trying. We have such an FPT algorithm to decide injectivity of one Mérieux layer, and one idea would be to somehow see if we can extend ideas from there. So somehow we need to use that the d-dimensional space is too small to do whatever you want.
Okay, then if there's no other question, you can. And the next speaker is, if I'm correct, is Gianmarco. Where are you here? So Gianmarco, native from, I forgot always, from Milan, right? Polytechnical Milan. Yeah. And he's going to speak about Bandit.
Yeah. Hi everyone, I'm Gianmarco. Today I'm going to talk about an open problem that is bothering me and my colleague Alberto since some time now. And the problem is about regret minimization in heavy-tailed bandits when the distributional parameters are totally unknown to the learner. So the setting is the stochastic K-arm bandit setting, in which we have a decision maker that has to take T decisions over K actions, and every action has a probability distribution which generates the reward. And the goal of the learner is, of course, to minimize the cumulative expected regret at the end. In particular, we are focusing on a setting called heavy-tailed bandits, in which we put an assumption over the probability distribution generating the rewards. The assumption states that the 1 plus epsilon order moment is finite and bounded by U, and we don't know anything else apart from this. So if epsilon is smaller than 1, of course, the variance of the distribution may be infinite. This setting has been introduced in a seminal paper from 2013, where the authors proved regret lower bounds for this problem, so minimum regret that any algorithm must suffer in this setting, as customary, both in a worst-case version and both in a version that depends on the suboptimality gaps. We can see how the two quantities, U and epsilon, which describes the behavior of the tail of the distribution, strongly impact the regret bounds. We know that the regret must scale in a certain way depending on U and epsilon. And the problem is that most of the literature, most of the algorithms that has been presented over the last 10 years, crucially relies on the knowledge of these two parameters. The problem is that these quantities are usually unknown in practical application, and from a theoretical perspective, you cannot even estimate them in a consistent way, especially when epsilon is smaller than 1. So many advancements have been made over the last years. There are many works for which the algorithm is assumed to be aware of both epsilon and U, and they managed to match the regret lower bounds presented in the first paper. There is an algorithm that is capable of assuming U unknown, but epsilon known, even though the regret bound doesn't match the lower bound. And then there is a really recent and rich literature about adaptive algorithms, so algorithms that don't assume to know either epsilon or U or both. And the problem is that there are some algorithms actually matching the regret lower bounds, but the problem is that all of them need some additional assumption that somehow substitutes the need for the knowledge of these two parameters. So there are some algorithms that have to know both of them, or either have to have an additional assumption that substitutes for this knowledge. There's a result from last year for which we know that the two regret lower bounds presented in the first paper cannot be matched if either epsilon or U are not known and no additional assumption is provided. The problem with these two lower bounds is that they are really qualitative, let's say. So they don't provide a sharp characterization of what should be like the actual best performance that you can obtain without this kind of knowledge. So this leads us to our first open question, which is formally stated that what is the best regret rate that I can hope to obtain if my algorithm doesn't know either epsilon and U or U, and without any additional assumption? So an algorithm that is totally unaware of all of this. Naturally, a subsequent question will be to, once I have this lower bound that characterize how much regret should I suffer without this knowledge, the subsequent question is, what algorithm can actually match this optimal performance in the adaptive setting? And also, there is a more broader question, okay, which is about the assumptions that have been made during the years to somehow cover for this non-knowledge of the parameters. And the question is basically, okay, I know that there are many assumptions that I can use in place of the knowledge of epsilon and U. But is there an actual best assumption, or an assumption that is strictly weaker than the others, or in some sense is better? I think that this also is an interesting stream. Of course, here I want to match the actual regret lower bound that was provided in the first paper. So here I'm trying to obtain a performance which is, as I know, epsilon and U, but with some additional assumption. we experimented many ideas during the last 1 year and a half. In particular, we tried to extend recent work, which is called Adaptation to the Range in K-arm bandits, which treats the problem of stochastic bandit with bounded reward distribution, okay? And the algorithm they propose is capable of actually adapting to the range without knowing nothing about the range, not even an upper bound on it. Interestingly, the authors provide a lower bound for the regret, which puts a relationship between the gap-dependent rate of regret that any algorithm must suffer and the worst-case rate of regret, which has this form, okay? So what we naturally tried to do was to put ourselves in a setting where U is unknown, so the actual bound on the moment is unknown, but epsilon is known. And our preliminary results show that you can obtain a lower bound that puts a relationship between these two rates of this form. Okay, so we see that there is an additional dependency on epsilon here in the exponent. And interestingly, if we set the worst case and gap-dependent rate to be the same, and in the special case in which the variance is finite, so epsilon is equal to 1, we get that the lower bound for the worst case rate is t to the 2/3. So we are currently trying to work in these directions, but also on some others. We are open and we encourage any of you to reach out if someone has any idea on how to further tackle this problem. There is a prize, which is an unlimited beers night in Milan provided by myself. And yeah, if anyone wants to reach out, we'd be really glad to discuss this further with anyone. Thank you very much.
Thank you. Any question? Yesterday, the price used to be your weight in Parmigiano, he said, but...
We can exchange it with Parmigiano if someone wants.
Okay, so any other question? I might have one, actually. Yes?
Do you have a guess what the lower bound should look like?
No. No, we only have, we have some scattered insights. We have these two lower bounds from last year's paper, but these two lower bounds are somehow weak. They are really qualitative. They just tell us that you cannot match that same lower bound as if the two quantities are known, but it's really hard to understand from here what should be an actual rate. We have this partial preliminary result that somehow relates the gap dependent and the worst case rate, but concerning the lower bound, we don't have much more than this, or any more than this, actually.
And for the upper bound, most of the algorithms are called UCP something. Do you think the issue is about estimating? Can you estimate, you think, this epsilon and u? Or
no.
There's no way of doing it?
Yeah, there's an old paper actually showing that there's a statistical limit. Yeah. There's some statistical impossibility results about estimating these quantities in general. We know how to adapt for the special case of Pareto distributions. So for for the special parametric case of Pareto distribution, the problem is actually solved because the procedure that was developed in the previous paper of last year can be translated for Pareto distribution without any additional assumption. But apart from that, we cannot really estimate those two quantities.
Okay, any question? No? Well, thanks again.
Thank you.
So the next speaker might be Yihong Gu, if he's here. No? So maybe we're just going to skip to the fourth open problem and go back to Yihong if he comes back. So the fourth open problem is given by Sasha Slimovic. You're here? Yeah, great. On data selection for a regression task.
This one? Okay.
Yeah.
Hi everyone, thank you for coming.
So this is a presentation of open problems that arise during our joint work with Steve Haneke, Shai Maran, and Mérieux Hudayev. The main paper I presented yesterday, so for those of you who also heard it, maybe some parts will be familiar already. So I will spend some time justifying why we should study data selection at all. So we have learning, and we can view learning in general as a union of algorithm and data on which we perform this algorithm. And while most of the research was focused on improving algorithms, creating new sophisticated algorithms, and so on, we shouldn't forget about data, and improving data sometimes improves the performance of your overall learning even more than some improvements of the algorithm. So with it, let's dive in our setting. So we have a general framework under which we studied in general a lot of different problems, but I will focus on particular ones where we have some open questions, and I will present them to you. Okay, so we have a data set D and a natural learning algorithm A, and we also include the teacher in between. And the goal of the teacher is selecting a small data set of size K. So we fix the size K, and after that we select some subdata set S in such a way that learner trained on this data set will be trained in the best possible way. And what do I mean by that is that the loss on the whole data set D will be minimized. Okay, let's explore our first example. So we have a data set in RD. It is just vectors of size D. And we select a subset of size S, and I will explain later what we do with this set. But first, let's understand what our optimal loss, which we cannot improve. So we have a natural loss given by just average of squared L2 distances from our prediction to points of the data set. And optimal solution here will be just average of the whole data set. Okay? What our learner does, it takes subset S and constructs an ERM. So our learner is an ERM, so it outputs just average of points of the data set S. It happens because of the fact that we are still minimizing this loss, and this loss given on a subdata set S will incur this particular average. Okay, and after that, we are trying to understand what is the best possible loss given by the subdata set of a fixed size. So here in the bottom, we have a formula, LD star of K. It is minimum over all possible selections of S of loss we are studying. Okay, so in mean estimation case, it is particularly easy to understand what's happening because of nice property we have that because the solution is the property of solution being close in distance to the optimal solution is the same as being close in total loss to optimal solution. So if we fix k equals 1, we need to select one point which is closest to average of the data set. And it is easy to show that this construction has such a property that a ratio is always lower than 2, and in some cases you can make it exactly 2. Okay. But for k equals 2 already, we need to consider not only points of the data set, but also pairs of 2 points from data set and their averages. And the optimal closest point will be the one that is closest to average of the whole data set, as you can see on the picture. Okay, I hope you understand the setting now. So this is what we know and what we don't know about this problem. And it raises our first question. what can we do about these cases for d equals 2 and larger? How can we characterize the ratio we've seen before? Okay, let me go to the second problem we have. Okay, so in a similar setting, we have a data set x1, y1, etc., xn, yn, coming from rd times r. But now, instead of selecting k points, we will select we'll select a set of size S from data set, and we'll consider all possible distributions over the set. So our support set will be of size k, but we'll consider all possible distributions. So in some sense, you can reweight your data points when you select a smaller data set. Okay, we have a loss that is natural in this case and is given by just normal squared loss in regression. And to explain it a little bit better, so if we are providing just 1 point, so k equals 1, the setting remains very similar to one with mean estimation, because reweighting doesn't help since you have only one data point. And you have the same result here, but for k equals 2 already, you can select any 2 points on the different sides of your regression, and reweight them in such a way that you will get the optimal loss itself. So, okay, in this setting, we understand what's happening we understand what's happening for k equal d or less. We understand what's happening for k larger or equal than 2d. We also have an idea, and it's not yet formalized, but we understand that for k equals 2d minus 1, it is as written here, but what happens in between is remain unknown. And yes, the most interesting particular case will be with k equals 4 and d equals 3. Okay, let me briefly explain why do we have 2d here. So why after 2d we get an optimal solution. So yeah, why does it imply optimal loss? So you can use this example for d equals 2, and you can understand that optimal regression here is given by w equal to 0, 0, but selection of any 3 of the points won't allow you to achieve this loss. And the reason why we have this 2d points is because of the theorem, which is a version of the Carthe-Dauderi theorem given by Steinitz, where we care not only about being inside of convex combination, but we only care about being inside of the interior of the convex combination. And because of there, we need 2d points to be able to construct this. We need, we need 2d points in order to get the optimal result in our problem. And the third question we wanted to propose is a general question which recovers both mean estimation and linear regression with some particular values of d and m. So we have some general linear function from Rd to Rm, and loss function is similar to one you would have in linear regression. And you can ask both in unweighted and weighted case. So by an unweighted case, we mean that we just select k points. In a weighted case, we select a support set of size k. And we ask a question, what can we say about the supremum of ratio of selection of k points with respect to selection of optimal solution? Yeah, that's it.
Any question? So this reminds me of corset selection, yeah. And it's the same, no? It's
yeah, right. So weighted selection is in some sense similar to corsets, and
for the first problem, if you have like a density, if D has a density on around the mean, then you have the ratio is converged very quickly, like exponentially fast with k or something like this, if I remember correctly.
Yes, there is some results regarding this, but we are wondering what will happen for the worst possible data sets out of all, and that's not the case that you have a lot of density near the average.
Any other question? No? Well, thanks again. And for the fourth open problem is Arnab. Yeah, you hear him? Great. Arnab it is that we're going to speak about Nash equilibrium.
Okay. This open problem session would be kind of motivating a new problem in the space of stochastic multi-arm bandits and game theory, and it's kind of based on a few of my initial works with my advisors Kevin Jemison and Lillian Ratliff. Like Kevin works on stochastic multi-arm bandits and Lillian works on game theory. So let me just quickly introduce 2 zero-sum games. So you have like 2 players, let me call it X and Y, and X has n different strategies, and Y player has m different strategies. And if X player chooses some strategy I and Y player chooses some strategy J, then X player receives a reward Aij and the Y player receives a reward minus Aij. So hence the sum being 0. And zero-sum games can be concisely represented using just the payoff matrix A. And a very important notion that's kind of studied here is Nash equilibrium. So essentially, it's like a pair of distributions, X star and Y star, over rows and columns, such that if any player tries to deviate from this pair of strategy, then they don't like improve their reward. So due to the classic von Neumann's minimax theorem, you can always like formulate zero-sum game as a linear program and find the Nash equilibrium exactly. So the setting that we are interested in is a noisy setting where we don't know the matrix A beforehand. And so the way we can kind of access this matrix A is by sampling some entry ij. And what we observe is Aij plus some zero mean sub-Gaussian noise. And the goal here is to kind of find some approximate solution. And one such standard approximate solution is the epsilon approximate Nash equilibrium. So on a high level, you just want to find a pair of distributions X and Y, such that if any player deviates from their strategy, they can only gain by at most epsilon. So the main goal here is to find an epsilon Nash equilibrium in the given game with probability at least 1 minus delta. And the goal is to minimize the number of samples that we require. So there is a near minimax optimal for this problem already. Like you consider, like, for example, 2 no-regret learners, let's say exp3ix from both sides. And you can take like n plus m by epsilon square if it is an n cross m matrix. So you require that many samples in order to find an epsilon Nash equilibrium. So what's the question here? Like in bandits, you have like similar minimax optimal algorithms, but the community has gone one step further, and they have studied instance-dependent kind of guarantees, where if the given bandit instance is easy, then you can find an epsilon best arm even more efficiently. So for example, say if you have n arms with means mu1, mu2 up to mu n, you can consider this to be a very special case of zero-sum game, like n cross 1 games. And typically, you have like instance-dependent gaps like delta I, which is the gap between the best arm and the ith arm. And if you're interested in epsilon best arm, you can throw in an epsilon there. And then it is kind of well established that the sample complexity of finding the best arm is like summation of inverse gap squared. So the question that we ask here is, like, in order to find an epsilon Nash equilibrium solution in a 2-player zero-sum game, what is the optimal sample complexity in an instance-dependent fashion? So if you characterize the complexity as h1 times log 1 by delta plus h2, and what are those terms h1 and h2 going to look like with respect to the input matrix A? And also the approximation parameter epsilon. So before one even tries to answer this question directly, I believe like one should answer some intermediate set of questions before they eventually answer the main open question. So to begin with, you can consider this simple but like equally important case where, say, you assume that your matrix has a unique Nash equilibrium such that the support size is K. So essentially the distribution is over K rows and K columns. So the game is kind of taking place in the yellow region, but we don't know beforehand that that's the place where the game is taking place. So there have been some results in this space. So for example, if you have K is equal to 1, so it is like essentially you have an entry which is least in its row and highest in its column. And you can ask what's the sample complexity of finding this entry. So you can similarly define like gap parameters, like gap between this entry and the rest of the entries. And turns out the answer is sum of inverse gap squared in this column and sum of inverse gap squared in this particular row. It's like kind of mimicking the multi-arm bandit algorithm. So for k greater than 1 case, where you can have like mixed strategy, can someone like find an algorithm which scales like k by epsilon square plus n plus m by delta square? So essentially trying to reduce the dependence on 1 by epsilon square from n to k. And in this case, we had some partial work, like for k is equal to 2, and if you consider like n cross 2 games, you can find a algorithm which scales something like this 1 by epsilon square plus n by delta square. And one can also show that even for the simple case of 2 cross 2, you cannot get rid of this 1 by epsilon square term. And for n cross m games in general, even such bounds are not known. But there are some hopes, like there have been some recent works, including one at Colt, which looked at instance-dependent regret minimization in zero-sum games. Another open question that you can consider, which is slightly different, is that what is the sample complexity to find the support itself, like where the actual game is taking place? Nothing as such is known on the sample complexity side, but we have an interesting result in the noiseless case where essentially, to find this k cross k support, it only requires like n times k to the power 5 queries. Like you don't know the matrix beforehand, but you can query one by one. And you just need to see n times k to the power 5 number of entries of the input matrix, whereas the input matrix has n square entries. And the lower bound is also like n times k. So yeah, so the hope is that we can inspire new works in the intersection of stochastic multi-arm bandits and game theory. Yeah, thank you.
Any question? Yeah.
Hi. I just had a question on what exactly do you mean by sample complexity? Like, what is the interaction protocol? Like, does the learner get to see the entire matrix?
No, it's just like if you, I kind of mentioned at the start, like you can sample an entry ij and you observe aij plus sub-Gaussian noise.
I see. Okay,
Yeah,
so
that's the interaction protocol. So
okay.
Number of times you have to do that.
I see. And you can only see one entry. You can't see like a column.
No. Just one entry.
Okay.
There's a paper of Yakov Pobyshenko that shows that if you want to get like epsilon Nash equilibrium, you can reduce the size. The support is actually very, very smaller compared to
Yeah.
to the. Yeah, I mean, for the second problem, it's not helpful, but maybe for the first problem, is that helpful? Or? if you can reduce the size of the support.
You mean?
Yeah, because here K is the support of the optimal.
Yeah, yeah.
But there is an epsilon optimal.
So what I think is that if the size of the support of the actual equilibrium is large, then that support dependence should kick in terms of epsilon square. That's just a conjecture, but I believe that's the case. So if the support of the equilibrium is k, then I believe the lower bound is also like k by epsilon square. Yeah.
Any other question? No? Okay, thanks again.
Yeah.
Is there a price? Is there a price for this? Okay, no price, so, but still, just the glory. And so there was a fifth paper, maybe you arrive, Yihongu. No, well, there's a fifth one, so anyway. So if you want to look at it, it's on the proceedings. It was, where is it? It's here. On structure agnostic minimax risk for partial linear model. So anyway, so if he's not here, we're going to conclude this session, and this leaves you, this leaves us 17 minutes. That's correct? Yeah, 17 minutes before the next session.
Qu'est-ce que je fasse? Hop, attends.